Welcome to this presentation of our recent work on non-local games on noisy quantum computers. I am Emanuele Dalla Torre from Bar-Ilan University. Bar-Ilan University is located in the suburbs of Tel Aviv in Israel, not far from Jerusalem. These are pictures of our beautiful campus, one of the largest in Israel. I was lucky to work with talented graduate and undergraduate students whom you can see in this picture, and also to enjoy industrial collaborations with several companies. This work is financially supported by the Israel Science Foundation. We work in the field of quantum simulations. Imagine that you would like to describe the properties of a large quantum system. As we all know, the size of the Hilbert space required to describe such a system grows exponentially with the numbers of degrees of freedom. How can we solve this problem? One strategy is to use a very large classical supercomputers. This approach has been very successful in describing the properties of quantum materials. Alternatively, one can proceed by approximations, such as analytical approximations, quantum field theories, or even combine approximations and numerical methods. Alternatively, one can follow the quantum simulation approach. This has been done very successfully in the field of ultra-cold atoms, where the idea, first proposed by Richard Feynman, was to use a quantum system to describe another quantum system. In this case, the dynamics of atoms on an optical lattice are used to describe or to mimic the dynamics of electrons in a material. What we would like to propose here is that quantum computers can also serve for this purpose, namely describing the dynamics of large many-body quantum systems. The main challenge is that there is a dichotomy between the idealized model of a quantum computer that we have in our textbooks based on unitary quantum gates and reality, such as in this picture, noisy superconducting quantum computers, or alternatively trapped atoms, trapped ions, or other types of platforms. In these platforms, the dynamics is non-unitary because it is affected by random, unknown, time-dependent noise. In order to solve this dichotomy, we need to bridge the gap between these two worlds, the idealized model and the reality. And this can be done in two complementary approaches. One is to try and improve the hardware until a certain threshold known as quantum error correction threshold is hit. After the threshold is reached, one can effectively cancel all the time-dependent sources and effectively obtain a model of unitary quantum gates. However, doing that for large quantum systems is still far beyond the reach of current quantum computers. Alternatively, we can improve our description of quantum computers by taking into account time-dependent noise. The big problem that the community is trying to embrace is how to characterize and quantify the noise in quantum computers. Here, I would like to propose an approach to address such a problem based on non-local quantum games. Non-local quantum games are extensions of Bell inequalities to systems of many qubits. In particular, I would like to describe the triangle game, which was first proposed by Bravi et al. In Science 2018, and then extended and explained in the Daniel and Miaka paper in PRL from last year. This is a collaborative game in which a number, at least 3 classical players are trying to win a collaborative game by satisfying certain mathematical rules. A quantum computer can win this game with 100% probability. In contrast, if the players are classical, so a classical game can be won only in 7/8 of the times, so only with 87.5% at most. Let me give you more details about the game. In the minimum realization, there are 3 players, hence the name triangle game. Each player has 2 qubits and is asked to select the value of each qubit. All these values, the 6 values, are then transmitted to a dealer, which will check whether the values satisfy some rules. The problem is that the rules actually change from time to time, and they are determined by 3 coins that are tossed, one by each player. So each player knows the result of its own coin, but does not know the result of the other coins. This is because within the game, the players are not allowed to communicate between themselves. As you can see here in this table, there are 8 lines. Each line is a different rule. You see that the rules change for each line. And the first column tells you what is the value of the coins that will deliver these specific rules. So depending on the value of the coins, the verifier will select the specific rules. Now, the rules were decided in such a way that the 8 rules cannot be satisfied by the same output. There is no output of the qubits that can satisfy all the rules together. If we take a single rule, that's not a problem. But if you want to satisfy all the 8 rules at the same time, all the 8 lines at the same time, that's impossible. Hence, the players need to find the best strategy that will allow them to win the game with the highest probability. And this is done by actually not satisfying the first rule and satisfying only the other seven lines. So that's why the classical game can be won only with 7 out of 8 times. So on average, it will be won up to 87.5% of the times, not more than that. As I mentioned, the quantum computer can win the game with 100% probability. How this is done? Before the beginning of the game, the player share an entangled state. In this case, it is the so-called cluster, one-dimensional cluster state that is realized by applying Hadamard and control Z gates on neighboring qubits. Then the players toss their coin as they are instructed and perform a measurement. The measurement is performed depending on the value of the coin. So that's the trick that the quantum players are using. They are performing a measurement. They are measuring X or Y depending on the result of the coin. So each player knows the result of each coin and hence decides a measurement basis. As we know, one of the principles of quantum mechanics tells us that when a measurement is performed in a given basis, an entangled state will be affected by the choice of the game. So although we are not transferring classical information between the qubits, nevertheless, the fact that I measure one qubit non-locally affects the other qubits. So that's why these are called non-local games, because they use the non-local property of entangled state in order to have an advantage. For a perfect quantum computer, this would deliver a winning probability of 100%. In the presence of noise, that probability can be lower, and we have used error mitigation techniques in order to try and balance the noise. The error mitigation is applied in such a way that each player mitigates its own qubit. As we mentioned, they are not allowed to communicate, hence we cannot mitigate all the qubits together. This would not be allowed by the game. But mitigating each player independently, this is still okay. Let me show you the results. I'm going now to show the results of 4 quantum computers, where the red line is exactly this 87.5% probability, which is the probability that can be won by classical players. So if a quantum computer is able to cross the threshold to demonstrate a quantum violation, this means that the quantum computer has shown quantum properties, or if you want, is using entanglement, is using quantum properties in order to have an advantage in winning a non-local game. The results that were presented in the first version of our archive preprint were demonstrated that none of the 4 quantum computers were able to show a quantum violation. As you can see, all these bars, even after error mitigation, are still lower than the 87.5%, meaning that no quantum effect or no quantum violation had been demonstrated. After we have published this preprint, we were contacted by the Honeywell Quantinum company, who proposed to realize the game on their newest version of the quantum computer, the so-called H1. In the H1 quantum computer, actually, a quantum violation was demonstrated. As you can see here, the winning probability of Honeywell H1 was higher, significantly higher than 87.5%. Hence, the Honeywell demonstrates the ability of using 6 entangled qubits in order to reach a quantum advantage. How about the other quantum computers? Can we show a violation also in that case? In order to do that, as you can clearly see from this picture, one would need to lower the bar. So to play maybe another game in which the probability, the classical probability is lower, so that they will be able to win that game. We have done that using a property of the cluster state. The cluster state is a state that is a mutual eigenstate of the so-called stabilizers operators. Stabilizers are operators that commute between themselves and square to 1. Hence, by knowing the eigenvalue of these stabilizers, one can uniquely determine the quantum state. In this case, for 6 qubits, there are 6 commuting stabilizers. One possibility is to measure the sum of the products of all the stabilizers. So one takes all the possible products of stabilizers, sums them up, and obtains an operator. For this operator, the ratio between the best classical threshold and the quantum one is 21 out of 64, or in other words, 83.5%. So a quantum computer that goes above that threshold will show a quantum advantage. As you can see, this threshold is much lower than the one that we have shown before. Actually, exactly 1/2 of that, of the previous value. In fact, researchers, and in particular Cabello, Gu, and Rodriguez in a PRA in 2008, have asked whether this particular combination of stabilizers is the best possible available one. And they found a combination that gives even a lower threshold. And that's the one that we have realized in our quantum computer, in particular using the IonQ quantum computer, for which a threshold of 78% was obtained, which is much higher than the quantum threshold. Thank you for listening.